Hello. Hello, everybody. Welcome to the Global Composite Experts webinar series. My name is Wenbin Yu, Director of the Composite Design Manufacturing Hub. This webinar series is to examine the history, present capabilities, and the future of composites with the goal of sharing the knowledge of composite science and technology that has been developed over the past 5 decades. This webinar series was initiated by the Composite Manufacturing and Simulation Center at Purdue University. We are located in the Indiana Manufacturing Institute. All of you are welcome to visit us. We launched the Composite Design Manufacturing Hub back in 2013 with the mission to convene and serve the global composite community by creation, education, and sharing of resources for composite design and manufacturing. The CDM Hub provides a very powerful website called cdmhub.org for the composite community to carry out this mission together. We envision CDM Hub to become the premier resource for composite design and manufacturing in the near future. This webinar series is one of the initiatives CDM Hub started as a service to the community. This webinar series is made available by the support of CDM Hub sponsors, including Dassault Systems, SciTech Solvay, and Anna Swift. We greatly appreciate their financial support for CDM Hub. We invite more organizations to join us to serve the global composite community together. This webinar will be recorded and made available on cdmhub.org, where we email you once the recorded video is available online. The presentation will last about 40 minutes and will have about 10 to 15 minutes for questions and answers. All the attendees are muted at this moment. Please submit your questions through the Q&A box. After the presentation, your questions will be read and answered. Next, I will ask my colleague, Professor Byron Pax, to introduce our distinguished speaker today.
I'm delighted to introduce to you Professor Francois Trochu. Professor Trochu is a mechanical engineering, a member of the Faculty of Mechanical Engineering at École Polytechnique de Montréal, where he has served on the faculty since 1990. He's published numerous papers in scientific journals and presented a large number of papers at international conferences and has also patents in his name. His research activities focus on the manufacture of high-performance composites using injection molding processes. These are the resin transfer molding, the SRIM process, VARI process, and also VARDA, and on shape memory alloys. The code PAM RTM software was developed originally by Professor Trochu's group to simulate the RTM process, and it has been marketed since 2001 by the ESI group. It is used by several industrial sectors in the automotive field, BMW, Ford, GM, etc., in the aeronautics field, EADS Aerospace, Mitsubishi, Dassault Aviation, Airbus, España, etc. And he has obtained his master's degree here in the United States at the University of Texas at Austin in 1975. After working as a consultant in various scientific projects, he completed his doctorate in 1990 at the École Polytechnique de Montréal in the field of numerical methods. His work has received over 7,000 citations. His Google H index is 43 and his I index is 123. So you can see he's clearly a global composites expert, and we are looking forward very much to his presentation today. Thank you.
So, thank you very much, Byron, for your kind introduction and for your invitation. I am now sharing the screen. Do you see the first slide? Is it okay? Can you just let me know if everything is all right for the slide for sharing the screen?
It looks very good.
Okay, good. So I begin. So today I'm really pleased to present our work on permeability in liquid composite molding. And actually, all this research was devised to validate the process simulation software that has now become PAM-RTM. So we worked in this area for a long time, and I just want to show two industrial parts on which we were involved with Safran Group. Actually, they are made by RTM. And RTM, as you know, probably is an injection process to make high performance composites in a closed rigid mold. And there are several other process variants that are connected with this rigid mold approach. And we will see in this presentation how permeability, this concept of permeability, can be adapted to simulate RTM and actually liquid composite molding. Another example of part made by RTM is this beautiful here bike, mountain bike. This is a frame made out of carbon fibers with here also the extremity, which was actually in glass fibers. This was done together with us in a collaboration with ETH in Switzerland in 1999. So let's start a little bit with philosophy, because what we always try to do in research is to model from experiment. So the first step is observation of the phenomena. And afterwards, numerical simulation is supposed to help us to validate actually the model and also to predict. So we come back to experiments. So how are we going to proceed to simulate mold filling in liquid composite molding? Well, first of all, we have a mold here, which is schematically depicted like that. And at a given time, we inject or we, at a given pressure or flow rate, prescribed flow rate, and we have an impregnated domain at a given time. And actually, to simulate mold filling, we need to have a model. So the first model that was used actually successfully for that work is Darcy's law. Darcy's law enables us really to predict at each time step the shape of the flow front and its progression in time during mold filling. And now, how are we going to present today this concept of permeability? Well, first of all, we will talk about process permeability, which is different from the classical permeability, actually, which is a saturated concept of permeability that is used in Darcy's law, especially in groundwater flows. Now, we will see also how this concept can be adapted to different LCM process variants, and with the goal of establishing a systematic connection of permeability with process simulation, which is so important for software validation. The background of this work is actually 30 years of research on LCM since 1990, with the previous 10 years since 1980 on groundwater flows. So this is really my personal background that I will try to sum up in a short presentation today. At the same time, we will try to better understand the principles that govern successful applied research. So what is permeability? Well, permeability is a parameter that depends actually on how quick you can fill a porous material. For example, gravel, it can take 1 minute, sand about 5 minutes, and clay 1 week or even more. And all these factors depend on the pore size. And for example, also you can consider permeability when you have air flowing through a filter, like cigarette filter, for example. And the order of magnitudes of these permeabilities go from 10⁻⁹ square meters to 10⁻⁻10 and 10⁻11 even in the case of sand. So permeability is really connected with a flow area. That's why it is measured actually in square meters. Now, the outline of the presentation, we will first present Darcy's law and the basic facts connected with this fundamental law in porous media. And then we'll present the different version of process permeability, like the rigid permeability, 1D flow, the extension to 2D in the case of an anisotropic preform, together with some software validation. We will recall the benchmark 1 and 2 results. And then we will extend this concept of process permeability to vacuum-assisted resin infusion, or what we call direct infusion. It's the concept of flexible permeability. Each time I will show some software validation. Then we will talk about KZ, true thickness permeability, also with the 3D software validation. It is important, finally, not to forget a very important software property that will be presented shortly. And finally, we can apply these concepts to resin infusion, direct infusion without distribution medium, and indirect infusion, where we will introduce a concept of apparent true thickness permeability. Finally, conclude. So let's start with Darcy's law, due to Henri Darcy in 1856. In the case of injection, we first start with a 1D injection here, where we have two positions of the flow front in time, at time T1 and T2. And Darcy's law simply states that the flow rate per unit area, which is Q here, is proportional to the pressure gradient in the cavity. And the two here numbers that appear here, the first one is permeability of the reinforcement and mu viscosity of the liquid. Actually, this law can be generalized in vector form as follows, where Q is a vector, K is a tensor, a 3x3 tensor, mu remains the fluid viscosity, and delta P the pressure gradient. So the concept actually of permeability here that we call process permeability is actually an unsaturated permeability, because we want to measure what happens when we fill a mold. Whereas most of the time, the standard concept of permeability is a saturated permeability, where the mold is full, and we want to study the flow rate here. What is the flow rate that comes out or that gets into the mold in time? And the outward flow rate is very often measured when we want to talk about saturated permeability. So how can we measure process permeability? Well, there are several methods that were devised over the years. The first one is the simplest approach. It's the unidirectional method, where we inject a rectangular mold in time. A lot of people wanted to go faster in the case of anisotropic preforms, which is actually, most of the preforms are not isotropic. And they devised some, let's say, mold to follow up the flow front in radial injections. So this was also done. In the case of transverse permeability, usually it's a bit difficult to measure the unsaturated process permeability. Usually people work with a cylindrical mold, and we measure, actually in this case, the saturated permeability. So the different concepts of permeability here go from rigid to flexible, and then we'll talk about the connection with preform expansion, and finally, apparent permeability in indirect infusion when we have a distribution medium. So 2D in-plane radial injections, as was just described before, is really a tensorial equation here, where Q is a vector, and we have here the expression of the permeability field, where K here is a triangular matrix, where the first two terms of the diagonal here are the in-plane terms of permeability, which we often call Kx and Ky, and K33 is the transverse term. So this here is the permeability matrix in the principal axis of the flow. What are the principal axes of the flow? Well, we'll have a look in the next slide, but before that, let's have a look just at the case of isotropic materials, where we, for example, random fiber mats. The flow front in the radial injection is usually nearly a circle. In the most common case of anisotropic materials, where K11 is different from K22, then we have an elliptical flow front. Now, measurement of permeability by radial injection is not easy. We tried a long time ago, we tried to relate that to 1D flow, and there are some difficulties, like, for example, depending on the injection pressure, or especially if we infuse the preform. At a low flow front velocity, we have a fuzzy here shape of the flow front, and it's not even always elliptical, because in this example here, for 2 times 80 seconds and 140 seconds, if we try to fit the flow ellipse with the perfect ellipse, the flow front actually with a perfect ellipse, we get 2 angles here which are quite far apart. The angle beta here is 16 degrees, and here is 28 degrees. So it is not easy from these kind of measurements to get a very good fit. And this is mainly due to the irregular orientation of the flow ellipse, but also it is connected to the shape and size of the inlet gate here. This was studied in a paper by Professor Gauvin a long time ago. So what do we do in our lab to measure permeability is really we rely on the 1D flow approach. In a rectangular mold, we measure the flow front velocity by observing under here the glass cover, by observing the different crossing times of the flow front with the central line here. And by doing that, we are able really to get reliable measure, because here with the 1D approach, it's a simple, the data processing is robust, and most importantly, we have a good reproducibility, less sources of errors. However, we need 3 measurements to get K1, K2, and the orientation angle beta of the flow ellipse. However, we have a nice here Gauss distribution of the permeability. Whereas with the radial experiment, it's expensive tool, we have a complex data processing. However, the principal permeability can be obtained from 1 measurement, but the reproducibility is not high. And we have also an influence of the size and shape of the inlet gate. So we have a much larger here distribution. And we could check that by comparing our results with the results of a colleague who had such an expensive device in a research project a long time ago. Anyway, So the 1D approach, I'm going to present it very shortly. It's in a rectangular mold. Here we denote by xf the position L of t at time t. And what happens with Darcy's law? Well, this is 1D Darcy's law here. And the conservation of the liquid mass tells us that dq over dx equals 0. So this is simply the conservation equation in 1D. And that means that d2p over dx squared equals 0. So the pressure field here is linear from the injection gate. Let's say if the injection pressure is set from this relative injection pressure with respect to the atmospheric pressure up to 0, we have this first approximation of the pressure field during the injection. So how do we measure? We have a special tool here with a glass cover, and we can, with that tool, with engraved here lines on the glass cover, we can really record the different positions in time of the flow front. And doing that, we have, from Darcy's law, we can get permeability here. Because the velocity of the flow front is given by Darcy's law as follows. The only thing we have to add here is phi is the porosity of the porous medium. So to integrate, we get this equation here. And finally, when we integrate, if we assume that k, phi, and mu are constant in the mold, then we will get this basic here model, which relates the square of the position in time of the flow front in a rectangular mold with this term here, the integral of the injection pressure. We call that the impulsion. And I think it can be important, although it doesn't always have a very, very strong effect, okay? We could neglect that, but we do it. We integrate pressure because when you want to make an injection at constant pressure, you set the pressure pot at the pressure you want, you inject, but the pressure is never always nice like here. There's always a small delay before you get the set pressure. Here is the injection pressure that is measured by the tool here, okay? And then from this injection pressure in time, you can get by the previous model that I presented. First of all, you measure the velocity of the flow front, so you get the flow front velocity here, okay? And then you can calculate at each position of the flow front, you can calculate here permeability, okay? So this is permeability here, okay? Now, this permeability here, the line that is here, is called the least square fit. And it's with this value that we calculate in red the position of the flow front. And if it matches with the experimental positions, we can safely consider that the experiment was okay. So it's a built-in check of the measurement in 1D. So we can afterwards, we can also, when we simulate work with equivalent saturated permeability, like the one in a planar crack here of thickness D, it's D squared over 12, or the classical, let's say, Poiseuille tube of radius R, the equivalent permeability is R2 over 8. Naturally, there are many equivalent formulas for different kinds of runners. In the past, these two values were very helpful for us. We didn't really need to go to much more complex terms. Anyway, so this is the way we measure permeability. And in the end, we get a model of permeability as a function of fiber volume content, because when we change the thickness of the preform, well, permeability is a decreasing exponential function of VF. So a very small change in thickness will create a significant change in value of permeability. And this is the kind of model, the experimental model that we get of permeability as a function of fiber volume content VF. Now, just to show a validation of this measurement in 1D, these are our old results, not published actually, that were obtained after measurement of permeability in a 1D mold with obstacles. So at 10 seconds, at 13 seconds, and at 14 seconds, we are really able to reproduce the shape of the flow front in time, provided that we can control the edge effects along the edges of the mold, along the edges of the obstacle here. So there are some techniques, experimental techniques to do that. We have to master them in order to provide this kind of validation. Now, 2D permeability is quite simple. We have a preform with different fibers along the X and Y axis. And the flow front actually will not follow the axis of the weft and warp. It will be at an angle beta with respect to one axis. And then we have an ellipse with K1 and K2 and this angle beta. And the way to measure this 2D permeability is simply by performing 3 measurements along 0, 45, and 90 degrees to get actually to identify the ellipse. So how do we do that? Well, we follow the proposal, we follow the work in this reference article here of 2007. And from the 3 measurements that we perform along 0, 45, and 90 degrees, we have enough information here to identify the permeability ellipse and to get K1, K2, and beta. So we've been doing that for years now, together with many industrial partners. I mean, it's a kind of procedure that is well validated now. Now, one interesting example here I want to show of anisotropic permeability is when you want to inject a 1D reinforcement with an angle, you don't get a straight vertical line, but you get a straight line with an angle. And this angle here is 57 degrees. And knowing this angle, you can proceed faster to get the permeability anisotropic values. You just need 2 measurements instead of 3. Anyway, this was published in this article. I think it's not easy to get this kind of flow. Really, it demonstrates the good understanding and mastery of Claudio Di Fratta, who was a PhD student in Switzerland, in Zurich, a long time ago. So another validation we did also with our colleagues in Switzerland is this one here, where we validated a 2D flow with a radial injection with obstacles. And we could actually match the simulation with the experiment when we added these 2 bars on the mold. Because there was, although it was a plexiglass glass or a glass, I don't remember exactly, but it was quite thick. There was a very small deformation here, even at 2 or 3 bars of injection pressure. There was a very small deformation that would give us the shape of the flow front, but not at the right time. So by adding these 2 bars, we could control the deformation better and really fully validate the procedure. Okay, now let's move to the benchmarks on permeability. There are 3 benchmarks actually. I will talk mainly about the first 2 benchmarks. The first one, there were 11 participants, 2 different preforms, and 16 different techniques were tested. 1D and 2D radial injections, saturated and unsaturated flow, constant pressure or constant flow rate injections. This was the preform. One of the 2 preforms was a carbon J986 from Excel, okay, which was an equilibrated preform. However, the fabric structure made it anisotropic. And here are the results of benchmark 1 here. You see the benchmark 1 results. Compare with benchmark 2. Okay, so why such a difference? Well, it took 4 years to complete benchmark 1. However, benchmark 2 with 13 participants, supported again by Excel. It took 3 years to complete the work with all the different universities. Here are the 2 universities where I'm working, actually, collaborating also with Spain here. The guidelines, okay, were adopted by all participants, nearly all, actually. A rectangular mold. We wanted to have a length over width larger than 3 and check that we don't have, let's say, more than 2% of change here in thickness. And we performed 3 measurements according to the article, and we follow actually, the guidelines actually are described in this article of 1996. Now, the results of benchmark 2 are here. I just presented the least square fit here before. The least square fit results are apart, plus or minus 20% apart, compare with a 14 times difference with benchmark 1. However, there are some participants here who are not in this range because they could not respect fully the guidelines. Again, for principal permeability K2, we have also a good result of about plus or minus 16%. Again, some of participants are out of the bound. So this demonstrates that without guidelines, the results are really in a very wide range. However, if we are careful in the way we measure, we can have consistent results, because we know that the preformed material has a certain variability, and let's say plus or minus 20% is not bad given the number of participants. In our lab, with a good experiment specialist who knows really how to take the measurement, we can be around, let's say, maximum of 15%, let's say, maximum of 15% or even 12% we can go. But with the whole team, we had to be around 20% maximum. Benchmark 3, people wanted to perform another benchmark. We didn't take part. So between 2016 and 2018, there was a revisited in-plane characterization benchmark based on 2D radial flows. I didn't look at all the details. What I saw is that the results still seem to be apart. What I don't want to, we didn't take part, and I didn't really made a thorough analysis on that. Now, let's talk about how we can extend this approach to measure permeability to vacuum-assisted resin infusion. VARI is when we inject under a membrane here. We seal the edges and we pull vacuum. And the resin pot normally should be under the table of infusion. And the resin pot, actually, the resin will flow through the preform, pulled by the vacuum pump. So how does it work really? Well, contrary to most processes of, let's say, resin infusion, are indirect infusion, in which we have a distribution medium here, which results in a true thickness flow. However, some people have developed special reinforcements. Sometimes you can even use a standard reinforcement to perform a direct infusion without the distribution medium. So let's see what we can obtain without a distribution medium. Here, we measure what we call flexible permeability in the same way as the rigid permeability, except that we perform a flexible experiment under vacuum. And by doing that, we were able to check with the industrial partner, Kaizen Technology and Fibre Design in 2001, that we could get a really good, let's say, reproduction of the shape of the flow front in time. It was infused from this line down to this vacuum here line. And we could even have a good, let's say, comparison between the calculated and the experimental field time of less than 3.5%. And we could even do something more. If you can have a look, okay, you will see that we could predict dry spots here. So finally, the company could solve that problem easily by setting up here a kind of flexible channel so that the flow would be accelerated along that edge. But this work, which was published in a paper by Jubo, you will have all the reference at the end of the talk. And this actually allowed us to validate the concept of flexible permeability. Now, KZ permeability, true thickness permeability, can also be important. There are different cylindrical tools to measure KZ permeability. There are people who have a different approach. And there was a benchmark on which we worked with many other people because permeability can be important in the case of thick parts, also in the case of a distribution medium in resin infusion, in compression RTM, and in flexible injection. So we believe flexible injection is important. So we took part in this benchmark. And after the benchmark, we realized that there were a lot of, let's say, inconsistency in the results that came from the design of the tool itself. So we prepare a first paper that is now published on the design of the test molds for cylindrical injection. And there's a second one that should be submitted soon on the data processing. And by establishing a correction procedure on KZ measures, we could relate very well the results obtained in the benchmark in Montreal and in Wuhan in China. So I think this can be an interesting approach. Now, a validation of 3D flow was done with the work using the PhD thesis results of Joël Bréat from Le Havre in France, where he actually performed some experiments here in a preform that was nearly isotropic in the in-plane direction. However, through the thickness, the flow front was different. It was more an ellipsoid. And by measuring true thickness permeability and comparing with simulation, we could get a quite really good comparison between the experiments and the predicted flow front in this cavity. So let's say now regarding to flow simulation, okay, we have shown some validation. We have shown different LCM process variants for permeability, which are adapted with different, let's say, injection approaches. But there is a very key issue concerned with simulation. If you want to solve a mold filling problem, usually people, they use the control volume approach, in which around each node you construct here in rows in red, you construct a control volume and you impose the conservation of the resin volume flowing through this conservation volume. You impose that in the equations of the approximated model. So this is the standard approach: control volume with an approximation of the pressure field at the edges here at the nodes of each triangular element. So this is the conforming finite element approximation. Here you have a pressure field basis function, which is 1 at node J and 0 at node I and K. And so around here, the triangle, you have three such basis functions, okay? The key issue in PAM-RTM is to use a different approach, which is called non-conforming, where we approximate the pressure field in the middle of the, let's say, edges of each element. And by doing that, this gives us a discontinuous, piecewise linear shape function for pressure. However, the flow rate is perfectly conserved between two elements. And this was demonstrated in this paper published in '93. And it's very important for the simulation of liquid composite molding processes, because if you know that the mold doesn't have any leak, the only thing you really know well is the amount of liquid you inject, because you can weigh that liquid normally. So you can really control that. And to test that and verify this concept, we injected here a 3D model. Okay, this is the mesh. We worked on a lateral injection here. And the different here, this shows here the injected flow rate at a given pressure, which decreases in time, okay? This here in red is the flow rate across the flow front at each time step. And in green, you have the difference between the two. You see that it oscillates with conforming elements. Whereas with non-conforming elements, this is the injected flow rate. This is the calculated flow rate across the flow front at each time. And the difference between the two remains 0. So the flow rate is perfectly conserved. And this is very important for, let's say, RTM flow simulation, because there are always some edge effects in the mold. And in order not to have to refine locally the mesh, it's much easier to work with this kind of approximation. Now, let's go to direct infusion. If we want to refine the concept of flexible permeability and predict the variations of thickness of the preform, we have here a setup, an experimental setup, where we infuse a rectangular preform. We have, let's say, pressure sensors under, and we have LVDT on top of the preform, okay? And by doing that, all that work was published in Polymer Composite actually very recently. It was just accepted a couple of days ago, okay? And how does it work? Well, first of all, what happens in resin infusion? Well, at the beginning, the dry reinforcement, when we have, let's say, a fiber bed infused under vacuum, the external pressure is the atmospheric pressure, PA. We have a vacuum pressure inside. So when the reinforcement is dry, the compaction pressure on the preform is P vacuum. However, during resin infusion, PA minus P vacuum is the pressure driving the flow. And according to Terzaghi principle, PA, the external pressure, is equal to PC, the effective pressure on the preform, plus P, the pore pressure. So when the pore pressure increases here during the infusion, okay, that means that PC here will decrease. That means what? Well, that means simply that the thickness will increase. That means that permeability will change. So in order to model all that, we have here a 1D testing bench with 3 LVDTs and several pressure sensors. And by analyzing the results of this experiment, we have also here, we have a balance where we measure the flow rate in time, Q, okay? Because we want to perform first a direct infusion, and after some time, we let the saturated flow establish itself. And by doing that, we're able to get the thickness here, shape of the preform, okay, in time, when everything becomes stable in the saturated flow. This here is, normally it should be negative because it's vacuum pressure. So this is the vacuum pressure here, which goes from 0, the atmospheric pressure at the inlet, to -70 in this experiment. And this allows us to get H at each position here. We get H. Having H, we can calculate Darcy velocity. And from Darcy velocity here, we get permeability. So by doing that, we are able to get a full permeability model that in all the experiments we perform at vacuum pressure of -70, -50, -30, all the permeability models we get superimpose. And with this permeability model, we are able to predict the position actually of the resin flow in time. So this is the position here along the x-axis, and this is time. So we are able to predict reasonably well, maybe not perfectly, but reasonably well, the position. But what is, I think, is quite important is that we predict also, let's say, the thickness variation in time. So these are the results for the thickness variation for the injection of a rectangular part of, let's say, constant or varying thickness. We also worked on a part, a real part, an automotive hood for this model. So this allows us really to get a way to predict in more detail what's happening in direct infusion. For example, when people want to use a Shomara kind of reinforcement in which they have built-in flow channels that allow you to perform an infusion without a distribution medium, we can refine here with this kind of characterization experiment, we can refine all the modeling. Now, very important, indirect infusion. You have here an experimental setup, a typical setup for resin infusion, where you have here in green, you have the distribution medium with lines, equidistant lines drawn on it. And you have up this position under this here distribution medium, you have the preform, okay? And you have the vacuum line here. And what do we do there? Well, it's all that was developed in a master degree of Zainab Gofti, okay? And we have here this kind of experiment that we perform is pretty easy because we have a plastic film in between the distribution medium and the preform so that we can measure by filming the top and the bottom actually flow, okay? We can film what's going on here. Let's say we can film what's going on in the distribution medium and in the preform, independently from the true thickness flow. So always with the same approach as for the 1D rigid flow or flexible permeability 1D, the same approach will give us actually, the same approach will give us a way, okay? First of all, we will get K in the distribution medium, then we get Kx in the preform, independently from the true thickness flow. With these values, using the software PAM-RTM, okay, we can identify a transverse permeability Kz, which we call the apparent permeability, okay? And the true thickness flow that we can then simulate with the software will give us these results, okay, which superimpose completely the flow front position in time in the distribution medium and in the preform. So that means what? That means that we have a way now to identify a true thickness apparent permeability that allows us to simulate the flow in resin infusion with a distribution medium, which I think what what's left now is to apply that to a real part. So if some people are interested, I would love to do that. Okay, I think it would bring a great, let's say, simple improvement, because what most people do, they try to guess. They try to guess a flow, let's say, in plane equivalent flow permeability. What people do, to my knowledge, many people try to guess the permeability that could be used for this kind of simulation. So anyway, we have to move on. We have to conclude. So process permeability in LCM is connected to each process variant. Several concepts of process permeability were introduced, like 1D rigid, 2D, anisotropic permeability. In thick parts, we need KZ permeability. For resin infusion, we can work with flexible permeability, or in the case of a distribution medium, with apparent KZ permeability. Now, in compression RTM, which is used a lot for nearly flat parts in automotive industry, we need actually KX, KY, and KZ, idem in flexible injection. So the concept of process permeability allows validating process simulation. It conducts simulations with experiments, is the best way, in my opinion, to move faster forward. And finally, we must never forget that the simulation that we use must respect the conservation of the liquid volume injected. So thank you very much for your time. And I would like to show that you will have these references for 1D, 2D permeability measurements. They will be available if you download the file. And also we have this concept of apparent permeability here that was developed in this article here. No, sorry, this is the, in this article, it is the preform expansion model connected with permeability. And in this article, we work on KZ permeability. Okay, so I think this is enough for today. Acknowledgement. All the graduate students did a beautiful work. I put the names of the main students in bold in the reference. We had so many academic and industrial partners. I cannot quote them. We have here in Canada, in Europe, in the US, and Canada, and also in Europe. So all the work that was done is really a result of many interactions with industrial partners. So we have time, I hope, for questions. Thank you.
Thank you very much. Thank you, Professor Trochu, and thank you to the audience. There's some questions. I'll field those first, just to answer a question that has come up. Yes, this will be posted, and as will the notes that Professor Trochu has referred to. So that will all be available on cdmhub.org. And I'll make that announcement one more time at the end. But first, it's an impressive list of companies that you work with. And I would imagine you've probably come across a question from companies who might be strapped on resources, asking the question along the lines of, when do I simulate and when do I just experiment? When do I just try it out? And when do I need to use modeling and simulation? Could you comment on that and perhaps share some of your experience and the counsel you would give to a company trying to determine how to invest their resources best in the technology?
Yeah, that's a very interesting question because we work with several companies like Lockheed Martin, Northrop Grumman. They came to Montreal. They had a problem. This was a long time ago, like, you know, it was probably in the 90s, end of 90s, you know. And Bell Helicopter, we worked a lot also. And afterwards, we worked with Safran and Dassault Aviation and SNECMA. And all the time, people, they need to validate the software. So they have a special preform material that they send us. We make permeability measurements, and then we simulate with them. And after that, once they have, let's say, get acquainted with the approach, then it's their job to continue as they wish, to do in the future, So we didn't follow up with all these partners. We know with Bell, we did a lot of, let's say, they used it quite a lot. Matra Automobile also in France. We know that SNECMA, Safran, they purchased 2 licenses from ESI Group after our initial work on the fan blades. Okay, it's the answer is probably you have to try, you have to get acquainted with your material and a way to measure permeability in such a way that you can predict. Once you have done that, then you can, let's say, use the software in a more reliable way, I would say. But it's always, it's always a kind of trial and error approach, with the software as well. But you can do so many more tests with the software compared with in the lab, So that's the gain.
There's a learning curve either way. Yeah.
Yes.
There are a number of questions about various aspects of input parameters, measurements, whether it be permeability, fiber volume fraction, obviously the influence of fiber volume fraction on permeability. And we're not going to have time to dive into each of those, and I'll send those to you by email. But maybe a general comment from you on when someone is starting to use and consider process simulation in RTM, to what extent do they need to do upfront characterization? To what extent do they need to just dive in and start with some general simulations and generally available numbers? And what's the guidance you would give to somebody who's trying to, again, start, they're committed to simulation, but again, don't know where to invest their time and their resources as far as getting those good inputs?
Yes, thanks for this also interesting question. Actually, you can proceed by performing a full, let's say, experimental characterization of permeability, in-plane permeability as a function of fiber volume content. And then you have all the information you need to devise a part by RTM or by flexible injection. It requires a little bit of work at the beginning, but once you have this information, you can move much faster. Now, I know that ESI has also information on permeability values for a series of, let's say, preformed materials. So we can start also with that. But there's another idea that also was used by some industrial partners interested in flexible injection. Flexible injection is when the mold thickness changes in time, right? And you can set that change in some way with some processes, maybe not with, let's say, indirect infusion, but with flexible injection, you can control the thickness of the cavity. And then when you do that, then this changes fiber volume content. So finally, you need a range of values of permeability as a function of fiber volume content, but you don't always need to have the exact value that for a given part, because of the design of the process itself. So that was another alternative. If anybody has further questions, I will be happy to interact later.
And we certainly appreciate that. I'm sure the audience appreciates it. And we, again, thank you, Professor Trochu. Thank you very much. We've enjoyed the hour we've spent together. We thank all the audience. We thank you all very much, the participants. And we'll look forward to joining everyone again on May 12th, so in a few weeks, with Dr. Wim van Peppegem from Ghent, where we'll talk about multi-scale modeling of damage mechanics. So we'll look forward to seeing you all again. And again, all of this will be posted on cdmhub.org, and we will send all of you an email, and we'll send these questions along again to Professor Trochu. Thank you very much.
Thank you. Bye.
Bye all.